So looking today at the second part of chapter 1.4, over functions, I want to go over a few other aspects of functions. Now, of course, we talked about the notion that if I have a function, I can define it just absolutely as a function this way. I can tell you that it is f of x. If I say it's f of x, then I'm telling you that it is a function. And if that's the case, this is something called function notation, and where f in this case is a generic name for the function. And I don't have to call it f all the time, though it is just quick and easy to call it f. Just call it function. That's it. Now, of course, the x is usually our input variable, and being in parentheses, it just means it's the input variable here. So the thing on the outside is the name of the function, and the thing on the inside is the function itself. And we don't have to always do this, as I said. I could certainly maybe have a function defined as the distance as being a function of time. And this is function notation as written. Time itself is the input variable. A lot of times for distance and time we use d and t as the variables, but there's nothing keeping me from writing out time and calling time the entire variable. So in this case, distance is a function of time. Another thing to say about that, or a different way to say it, is that distance depends on time. Distance depends on time. This is the notion that if distance depends on time, then time is independent. And distance is dependent. So when we're talking about what is the independent versus the dependent variable, the independent variable is always the input. The input is always independent. The output of such a variable, being distance, is going to be the dependent variable. Remember, if we have functions, we can relate them to machines, to where we have an input and an output. And in this case, our function name would be f, our inputs would be x's, and our outputs, oftentimes we would call y's, or we can call them literally f of x's, where f of x represents on the whole the output of the function. There are several different types of problems that we should be able to work as it relates to function notation, such as if I give you a function and I define it as such by using function notation, then here is an example of such a function. This is known as function f. Literally, this is function f. And if I were to ask you for f of 2, what I'm saying here is to input a 2 and evaluate the function. Now, you probably should understand that in order to do this, all I do is plug it in everywhere I see an input variable. So in this case, I would get a 2 squared, which is 4, put a negative in front of it. Order of operation, you have to be careful here. And then, I yield a 5. So for the value of f of 2, I produce a 5. Easy to see. What if I want you to produce a f of t? And that is, in my original function, is, again, that one right there. Well, what do? Well, all I have to do is input t. So everywhere there was an x, I now input a t. In other words, just because I put a 2 in the parentheses and I input a 2, there should be no real issue if I put something else in between the parentheses. I will just end up with something that still has variables. Essentially, I've changed the variable here. What if I do this? What if I have you evaluate g of 5? Well, certainly you can just put 5 into the function, right? Well, this is true, but in this case, I just don't know what g of 5 is because I do not have a g function. I only have an f function. So things like that you need to be aware of. If I change the function name by using a g, then obviously I need a function called g in order to perform that operation. I could very well do something like this. Evaluate f of x plus 2. At which point, everywhere there's an x in my function, I am going to plug in that value. And I think one of the best ways to do this is to go ahead and leave blanks for x where I need to input that value. So if that's the case, then I put in my blanks. Now I input everything in the parentheses in both places. And then when I go to evaluate this, what I would be doing is I would FOIL this out, distribute the negative, distribute that, collect all the like terms. And if I do it correctly, I should end up with, and I'm going to shortcut this for the sake of time, I will end up with a reduced output. Now notice that I have it doesn't produce a number per se or a numerical output because I am still changing or inputting a variable into the function itself. But everything that is in the parentheses replaces whatever the input variable is in the original function. Now, why is this useful? Why is this needed? Because here, think about a scenario whereby I give you a function and what if I wanted you to evaluate a function for like 20 different input values? What if I said, all right, here is my function. Please give me the outputs as follows. Tell me what the output is if the input, what is the output if the input is 2? And then let's say I want another one, and I would have to say, what is my output if my input is -10, right? See, I would have to verbalize all that. Every time I wanted to get an output for a given input, I would literally have to verbalize it. But the beautiful thing about function notation is that all I have to do is do that. And it is very much implied that what my task is to put 2 into the f function and evaluate it for its output. If I ask you to do find the output when the input is -10, all I have to do is put a -10 in there. So we have no reason to be afraid of function notation because it is intended to not only define functions absolutely that these are functions, but it also signifies to us a better way of doing our math. Because now I do not have to be so verbal in giving you the instructions. Absolutely, with a few marks on the page, I can tell you to evaluate a given function for a particular input. And I do not have to worry at all about misinterpretation here. Now, if that's the case, then certainly there are other types of things we would want you to evaluate. For example, what if I asked you to evaluate the following function, or evaluate f of x when it is equal to 0? In other words, in this case, I would be interested in knowing for a given function, let's say I have 2x or x squared plus 5. And if I want you to evaluate this for a function where the function is equal to 0, then what I'm essentially saying is, and remember, f of x itself represents the output. I want to know every value of x where the output is 0. Well, we know traditionally that the output itself is the y value. So all we really do is replace the output value with a 0. And then, of course, we solve the problem. Now, you'll probably notice here that I ran into a little bit of an issue with the problem that I chose. However, it shouldn't be too big of a deal. And later we will see that this is the same thing as saying I square root of 5. Right now we'll probably avoid the negatives under the radical and the imaginary numbers. But for right now, just understand that if I'm asking for an output, and if I say the output is equal to 0, then what it means is I replace f of x with 0. It's essentially taking the zeros of the function. It's finding x-intercepts. We'll make that connection later as we go through this. Another thing that we would be interested in doing is to evaluate the following. And let's say I want you to evaluate when f of x is equal to g of x. For example, let me give you an f of x, and let me give you a g of x. Two different functions. Got to pick a right number here. I'm doing this in my head. Okay, so if this is the case, then what I would be interested in doing is to say, all right, how do I evaluate what x is if I tell you that the two functions are equal to each other? So if I assign you a problem like this, then it should be readily apparent what your task is going to be. You are literally going to set these functions equal to each other. So if f of x is equal to x squared, then and g of x is equal to x plus 2, then all I have to do is set them equal to each other, and then I solve them. Of course, if I solve an equation like this, you probably should understand what needs to be done here. I need to evacuate one side so that I have a 0 all by itself on that side. And now I can solve by a variety of ways. And we'll talk about quadratic solving later. But if this is the case, then I probably should realize that this factor's like this. And therefore, I would apply what's known as zero product property to get the solution. Don't freak out if you're having a hard time remembering how to solve your quadratics. We will get up to speed on that. But there are two solutions here. So if I were to look at this and say, all right, evaluate this when f of x is equal to g of x, then this is what I'm looking to do. Maybe another type of a problem would be to do something very similar, but instead of giving it to you as an algebra problem, maybe I want you to evaluate it graphically. In other words, perhaps maybe our graph looks like this, and maybe I give you a certain function. Let's give you a line, horizontal line. Let's call that f of x, and then let's call get a different color here. Let's call this g of x, and then I ask you to evaluate many different things. Where is f of x equal to g of x? Where does this occur? Well, certainly it occurs where they cross, right? This is where they are absolutely equal. So if this happens to be the point 2, 3, then this occurs when the output is 3. How about if I were to ask you for where does f of x, where is it greater than g of x? Then you probably recognize, well, this portion of f of x is higher up than g of x at that point, from negative infinity about to where 2 is. And if this is the case, we always want to use the input variable to express where that is. So where is it greater? It is going to be greater from negative infinity all the way to 2. when using what's called interval notation. I can say this a different way, certainly. I can also say that this will occur when x is less than or equal to 2, if that's the case. Actually, less than 2, because when it is 2, they're equal to each other. So when x is less than 2, this is where that occurs, because f is bigger than g for all values when x is less than 2. We're always going to use that x value to do that. By the way, we would have done the same thing here. We would have said this is the case when x is 2. And so we use the input value to determine where those intervals occur. Another way to do this would be to say something like, well, where is g of x greater than f of x? Which areas on the graph does that occur? And of course, I can circle all that right there. That's where our g function is higher up than our f function. So if I were to express this in a certain way, then I would say it occurs when x is greater than 2. Important to really follow and understand. The last thing I'd want you to be able to know is the notion of domain and range of functions. If I am interested in problems making sure that functions truly are functions, then I need to, in some cases, limit my domain or restrict my domain in such a way to assure that it produces reliable outputs. So when we talk about domain restrictions, those domain restrictions will oftentimes happen in 2 different types of equations for us. And these are the major ones. The first type of equation the first type of function that we need to be aware of that is going to require a domain restriction is in any situation where we could possibly put 0 in the denominator. This is something we have to avoid. If functions are actually machines, then we are relying upon the machine to produce a very real output. The problem with this is that if x is 0 here, if x is equal to 0, then it will not produce a real output because 1 over 0 is undefined. So anytime we are dealing in functions, we have to avoid scenarios that will make the function undefined. So if this is the case, then we can rest assured that that this can be any number we want, except for we cannot input a 0. So the domain restriction here is a 0. And so the way we normally will present this, and we can present this in several ways. We can call this all real numbers, except x cannot be equal to 0, whereas that's my domain restriction. I could even put this in some sort, and I'm really not picky about the different notation that you will use. You can say it goes from negative infinity to positive infinity, except x cannot be equal to 0. Or you can say it this way. X can go from negative infinity to positive infinity, yet x cannot be equal to 0. These, in these cases, are the restrictions to the domain. These allows us for this is what allows us to keep this as a function. Because if we allow a 0 into the function, it would not work. It just would not be practical to us in those scenarios. The second scenario by which we need to understand is a scenario when we have not x's in the denominator, but perhaps an x underneath a radical. When we have an x underneath a radical, let me go ahead and give it to you a little bit more there. Let me make it a little harder for you. When we have an x underneath a radical, we have to concern ourselves with again, outputs that are unreal in nature. Because we know one thing, right? We cannot have negatives under radicals. Negative under radicals are no-nos if we are concerned about keeping and preserving real numbers. So obviously it becomes a question of figuring out what it is that makes underneath the radical less than 0. If you want to know the best way to do it, I just absolutely, if you want to know what makes it 0, that's the good place to start. So the best way to do that is take what's under the radical, set it equal to 0, and just solve. And what that means is that what's going to be under the radical will be 0 if you input a -3. And I think it's clear to see that if I input a -3 here now, then I would have the square root of 0, which evaluates as 0, and that's fine. But notice that 0 serves, in this case, 0 is the border line. In other words, I can't allow anything less than the square root of 0. Even if it's if it's -0.00001, that is going to evaluate as an unreal number. So I have to be careful there. And so, but this gives me my little border here. It tells me exactly where the breaking point is for this function. In other words, as long as my x values are greater than or equal to -3, then this absolutely works. That's a domain that works for me. And notice here that if I go less than, if I'm equal to -3, or excuse me, if I'm less than -3, then what's going to happen is I get bigger negative numbers there, which is kind of a faux pas. But still, if I get bigger negative numbers there, then obviously I run into some issues with negatives under the radical. So that's the key here. Figure out what makes under the radical 0 by setting what's under the radical equal to 0, solving, and that tells you the border line. And then it's just a question of figuring out, well, are numbers bigger than -3 safe, or are numbers less than -3 safe?